Apologize. Sorry.
Yeah, Davide, are you here? Okay, here he is. Well, it's a great pleasure to welcome Davide to this session. And Davide, you will give the grand finale talk. So thank you very much and go ahead.
Thank you very much for the opportunity to speak. I would like to review, in general, some of the things that have been done in the subject of twisted holography. And in particular, I will try to discuss in detail a nice example that I've worked out with my student, Kaja Budzik. But the part of the work that I'm going to describe that I did was done in collaboration with Kaja and with Kevin Costello. Okay, so twisted holography. I use this term twisted holography to denote a general program based on the idea that a lot of the examples of holography that you know involve supersymmetric quantum field theories, and the supersymmetric quantum field theories admit twists, which are ways to sort of separate out a consistent subsector, a protected subsector. And so in principle, it should be possible to match precisely a given subsector of a quantum field theory with a protected subsector of the holographic dual theory. And of course, this is something that has been done from the very beginning of holography, because typically protected subsectors are the only places we can do calculations. But the element which is novel in twisted holography is that you try to use this technology developed by people like Costello and his collaborators to really write down a self-contained twisted theory which captures the whole protected sector in the form of his own sort of quantum field theory. So he tried to define a simplified quantum field theory which captures only the protected subsector, and to match it with an actual simplified version of the theory of supergravity. And so this offers novel perspectives on all calculations, but also allows you to do new calculations. I should also say that this subject has some very interesting resonance with the sort of topics that Professor Gopakumar described on Monday, in the sense that a lot of the calculations done in the context of on the quantum field theory side of twisted holography involve essentially free correlation functions, because in these protected subsectors, the coupling is essentially turned off. And so, but on the other hand, as I said, you get sort of full toy models of holography where these free protected calculations are dual to actual holographic setups. And so it must be possible to extract these holographic dual geometries just by staring hard enough at free correlation functions. Essentially, in general, in the twisted holography setup, things like the Hooft coupling drop out, and all you're left is sort of the combinatorics of the large N. So on the gravitational side, there is a 1/n expansion, and that matches something that could be the Hooft expansion in the gauge theory in sort of string theory examples, or something more complicated in M theory examples. So what does it mean twisting a theory concretely? So this is something you can do whenever your supersymmetric quantum field theory admits an nilpotent supercharge. So you just need one of the supercharges to square to 0. This is often possible, not always. For example, if you have 3D n equal 1 supersymmetry, it's not possible to find the nilpotent supercharge. But most quantum field theories supersymmetric quantum field theories admit such a supercharge. And then you take the supercharge and you add it to the BRST differential for your theory, which essentially means that you're passing to the cohomology of the supercharge. And that what simplifies the theory. And essentially you just process the whole theory with this new BRST differential using the deformalism, and you can do simplifications because you can add and remove few exact terms and things like that. And at the end, you get sort of simplified, consistent quantum field theory. The resulting quantum field theory is typically topological or holomorphic, in the sense that when you pass the topology of supercharge, all the translations which are in the image of the supercharge become exact. So you lose those translation generators, the correlation functions, the theory becomes independent of those translation generators. Correspondingly, you lose some components of the stress tensor that become exact. And so your theory will not depend on the full metric on the space-time, but only on some parts of the metric. And so in some situations, this might be enough to just remove completely the metric dependence, in which case your resulting theory is topological. But in a lot of situations, it sort of keeps only the complex structure. So most of the twists that you have available in situations of low supersymmetry, for example, are holomorphic twists. And I have to say, to open a parenthesis, holomorphic twists have not been studied much in the physics literature, but I think they are potentially interesting. For example, holomorphic twists are available in 4D n=1 gauge theories, where we don't have topological twists. And I think it would really be nice to know if these twists can really tell us anything about the physics of these low supersymmetry quantum field theories. Again, in an holographic context, this is sort of related to efforts of studying things like 16 BPS states in nickel 4 supermills. There have been several efforts in the past to sort of understand this minimally protected subsector of nickel 4 supermills and match it to holographic calculations, sometimes with quite some success. And this sort of thing can be sort of encapsulated self-consistently in a twisted holography calculation. Now, in another thing I should mention, right, so sometimes you can do something like omega deformation, which also reduces the number of dimensions of space-time. So, for example, you could take a 4-dimensional theory, but extract a 2-dimensional protected subsector. So this is the best understood part of the process. As I was saying, these manipulations of the quantum field theory should be something that you can match on the supergravity side. And so it should be possible to match this twist of the supersymmetric quantum field theories to some protected subsector of supergravity, something you could call twisted supergravity or twisted superstring or twisted M theory. So Costello has conjectured a variety of descriptions of possible twisted supergravity theories. And so this gives you a way to propose possible holographic duals. Although the analysis is not quite finished at the moment, there is sort of a lack of a precise prescription to take a supergravity solution and map it to a twisted supergravity solution. And I think understanding how to do that will be really useful to progress in various directions. And take this as an invitation to people who know supergravity very well and BPS configurations of supergravity to perhaps give a look at the twisted holography setup and try to figure out how to integrate this knowledge with the twisted supergravity approach of Costello. So in my talk, I will discuss a couple of examples. But yes.
So why does the usual method fail for supergravity, like considering a certain supercharge and setting it to, by twisting it and setting it to 0, why does it fail for supergravity?
Oh, well, so
you're saying that supergravity.
Mm-hmm. So on the supergravity side, you do something similar to slightly different. So on the supergravity side, the supersymmetry is not global. It's a gauge symmetry. So you cannot just say, okay, take the supercharge and add it to the differential. You can do something, so Costello's perspective, instead you can do something that is a bit unusual physically, but seems to work, which is to give an expectation value to a bosonic ghost, which essentially has the same effect on the VRST charge of the theory. And then you do perturbative calculations around this new background.
Okay.
But yeah, so for example, I don't know, when you do certain twists of type 2B string theory, the result is the B model, BCUV theory in 3 complex dimensions. So in principle, you're studying essentially 𝗬𝗊𝗀𝗀𝗀𝗀 geometries in 3 dimensions. What would be nice to be able to do would be to take an actual supergravity solution like LLM and extract from it a 𝗬𝗊𝗀𝗀𝗀𝗀 geometry to be used in twisted supergravity, twisted holography. And it's actually, I've been actually trying to do that for the last month, and it's painful. And I think that somebody who knows supergravity very well could do this sort of translation much better. So this sort of, there is all this literature on the how do you call it, special geometry, where you take your killing spinner, extract a variety of forms and geometric objects out of it, and you constrain your supergravity solution. That same data should be something that can be translated into the twisted supergravity background. And I think it would be very nice to do so. Anyway, so once you manage to identify both the twisted supersymmetric quantum field theory and the twisted supergravity background, then you get yourself a simplified but self-consistent model of holography, where everything is potentially computable and can be done in a mathematically rigorous way. So it's a setup where you can literally prove an example of holography, a complete example of holography. And as I was mentioning, there's a lot of the calculations in the quantum field theory side are essentially free field theory calculations. This might also give insight on how to extract a geometry from free field theory correlation functions. So how geometry emerges from large and limit independently of the coupling. There have been some nice mathematical work done on this topic. This work is sometimes called holography, or perhaps in a physical language would be more properly called pre-holography, in the sense that it focuses on understanding in detail the effect of the twist on the coupling between the bulk string theory, M theory, and the Word volume theory of D-branes. Once you understand this coupling in detail, then, which is done in flat space essentially, then the presence of the D-brane, of course, back reacts the geometry in some way, and one can follow this back reaction perturbatively and sort of get information in order by order in N, and then use mathematical technology to actually bootstrap this to all orders in N. So you get situations where you can really compute the OPE of various types of OPE, depending on topological or holomorphic setups on the quantum field theory side, and match it with calculations done in the twisted supergravity. Costello worked this out in some beautiful examples in M theory, sort of studying the volume theories of and choose on fibranes and their sort of omega deformed topological twists, and matching them with calculations done in a beautiful twisted M theory theory, which is defined by sort of 5-dimensional Chern-Simons theory. And there was also this group of Istiak, Musavian, and Zhu, which did beautiful calculations involving interfaces in equal force superior meals. But I was saying these derivations focus on the OPE or local operators and work effectively perturbatively in N, not in one over N. It's kind of funny. You're sort of turning on the effect of the D-branes order by order in N. And the reason this can be sort of made sense of in the Lagrangian limit is that these OPEs are often polynomial in N. And so you can study a polynomial starting from the leading coefficient or from the first coefficient, and it works both ways. In the sort of work that I did with Costello and with Kaja, I was trying to study situations where instead working with a non-perturbative back reaction really matters, so that you have a full, you're studying a fully back reacted setup. So you really have the analog of ADS 5 times S5, say, matching the twisted quantum field theory calculations. And so that's what I'm going to discuss next. Any questions before I get there?
I was just wondering whether you can take the zero mode of the supercharge operator for supergravity and consider the twisting or something like that, because the zero mode would be some charge, right? I mean, it would be because the local supercharge, you can always make an expansion in terms of the moments which would each correspond to some version of supersymmetry. And maybe the zero mode can be considered as a global charge, global supercharge, right?
I'm not sure. I mean, clearly in a holographic situation, there is a supercharge, sort of a global supercharge, because of the local gauge symmetry in the bulk. It's restricted to the boundary. But I'm not sure it would have the same effect. Also, in holographic language, I think that in an holographic language, adding the BRST charge, the supersymmetric charge to the BRST charge, really maps to the holographic dictionary to turning on a web for the super ghost. But that's all I know at the moment. I'm not sure I can give a good answer. Sorry.
Okay, fine.
Okay, so I'm going to focus for the rest of the talk on a certain subsector of N=4 supermills called the Caladron Subsector. This was introduced for the N=2 theories by these authors. So for any 4D N=2 theory, you can extract a chiral algebra whose correlation functions capture some of the correlation functions of the 4-dimensional theory, superconformative theory. In this original work, this subsector was introduced as a cohomology of a peculiar combination of supercharges and superconformal charges, but it's possible to reformulate it as the result of an omega-deformed holomorphic topological twist, which sort of puts it more clearly within the twisted holography setup. Concretely, what are you doing? You take 4 of the scalar fields on N=4 supermills. I denote them as phi plus minus plus minus. You restrict them to live on a plane, but you also take position-dependent linear combination of these scalar fields in such a way that their green function becomes holomorphic. Essentially, once you put the operators on the plane, the green function becomes something like 1 over absolute value of z squared. And if you take position linear combinations, which depends on z bar, in such a way that you get a z bar at the numerator, you end up with a correlation function that looks like 1 over z in the free theory. But the magical thing is that this is then not affected by coupling. So this chiral algebra subsector has a correlation function that can be computed in the free theory. For the case of N=4 supermills, it looks like a chiral 2-dimensional gauge theory coupled to 2 adjoint scalar fields, which behave like a beta gamma system in 2 dimensions, or symplectic bosons. As I said, the correlation functions are computed essentially in the free theory. The only effect of the gauge coupling or the gauge interactions is that it gives a certain projection on gauge invariant operators that we'll discuss momentarily. And the holographic dual of this chiral algebra was identified in my work. Well, actually, in a sense, you could say that the dual was proposed in a paper by Dijkgraaf and Waffa, where in the paragraph they proposed that they proposed this chiral algebra, which is they discussed the fact that this chiral algebra appears on the volume of the 2 branes in the 3-dimensional B model, and they suggest that perhaps it could be dual in some sense to the B model on the deformed conical. So indeed, the proposal is that the Caladron subsector is dual to the bimodal on SL2C, which is the deformed conifold. And then the local operators of the chiral algebra coupled to dual to fluctuations of the compact structure of SL2C near the boundary. Now, as I mentioned, the precise dictionary between supersymmetric solutions of type 2B string theory and deformations, Calabi-Yau deformation of SL2C has not been worked out in detail, but it would be very nice to do so. Now, in the gauge theory, you essentially build local operators out of these two fields X and Y, and of the ghost and some BC ghosts with a Beresty charge, which is might be familiar from two-dimensional conformative theory. Essentially, it's a Beresty charge that makes the current in the Beckhammer system exact. You can compute a cohomology in the large N. You find 4 towers of single trace operators, which are sort of super partners of traces of linear, super symmetrized traces built out of the X and Y fields. And you can develop a precise holographic dictionary, which matches these local operators to specific deformations of the compact structure of the boundary. And so in principle, you can do calculations where you take a 4-point function of these local operators and you try to match them with the bimodal topological strings in SL2C. By the way, the bimodal has this nice property that after it's a topological string theory, it is also a local quantum field theory in a sense. So I mean, the string field theory for the bimodal has a finite collection of fields, and it's called the Kodara-Spencer theory. It is a theory which is not renormalizable in principle, but Costello and Lee shown that it is actually has a unique renormalization if you require it to be coupled to D-branes. So calculations can be done in the bimodal topological string or in this BCOV theory, and essentially do Witten diagrams in SL2C. So with Costello, we proposed so that one of the key ingredients of defining this, of making this duality work, is really to find what are the correct holographic boundary conditions in SL2C. Which boundary condition can you put on the BCOV fields in SL2C so that the boundary deformations are precisely dual to the operators of the chiral algebra. So with Costello, we defined the boundary conditions, and we verified that indeed the boundary deformations of the boundary conditions are in one-to-one correspondence with the single trace operators. And also we verified that the leading in N, so both sides of the duality have very large symmetry algebra and the large N limit, and we match it. And this is enough to show that things like the leading N contribution to the leading N 3-point functions match on the two sides. But it would definitely be nice to push this further and to study in detail the 1/n expansion with correlation functions and match it with the Witten diagrams in SL2C. Or perhaps even better, to find a way to derive the worksheet theory, the bimodal, out of the Hooft expansion of these correlation functions. I think that would be fascinating. In the work with Kaja, we tried to identify a situation where we could study non-perturbative aspects of this correspondence. So, because I mean, ultimately, I think I find fascinating about these crystallography examples is that potentially you can learn things about the saddle expansion, the expansion of semi-classical saddles in Gravitons string theory. You can learn non-perturbative information in the sense that if you look at intricate enough configurations on the gauge theory side, you might be able to find situations where on the holographic dual side you have a sum over different geometries. And then it would be nice to see, which criteria do you use to determine which geometries contribute, what sort of Stokes phenomena are there, and things like that. Now, we are definitely trying to study a situation where there are multiple geometries. But for now, with Kaja, we studied the toy model where the geometry is still S2C, but you have multiple, but you have D-branes in the bulk, and there is a sum of different D-brane geometries. Sort of. And this is what I would like to discuss in detail for the rest of the talk.
So you don't have some sorts of wormholes or something? No.
Sorry?
In the bulk?
Yes.
You don't have wormholes or things like that in the bulk?
I don't know. Honestly, I don't know. So it would be very nice to figure out which sort of Calabi-Yau geometries appear in the dual of a variety of different correlation functions. There are many things one can do. First, I mean, the most obvious thing is to just insert local operators, which are built of order n squared fields, and which can sort of create an actual macroscopic deformation of the geometry near the boundary, and then see how this deformation, is filled in by actual Calabi-Yau geometries. But I think this toy model, I mean, it should be possible to use this toy model to explore a variety of phenomena in holography. Although, to be honest, I never quite know if what has been learned has to do with supergravity or with superstring theory, because of course everything that is computed is independent of the Hooft coupling. So it's possible that some of the phenomena you observe are actually associated to string theory in a strongly curved DS rather than supergravity in a weakly curved DS. It's hard to know. Still, no perturbative information about either string theory or supergravity should be interesting.
And what do you think the corresponding boundary theory would reflect of these wormholes? Something like what matrix models JT gravity duality have uncovered, something like that?
Well, one thing that is kind of interesting is that you can embed all matrix models inside this chiral algebra. So if you look at 2-point functions where you put complicated operators at 0 and at infinity, those 2-point functions are actually computed by a 2-matrix model. So I don't know, it's possible that some of these toy models of holography can actually be integrated within this twisted holography setup. So I could imagine engineering a 2-matrix model and then pushing it to criticality and seeing what happens in the dual geometry. I'm actually trying to do these sort of things. There can be connections. Again, diagraph. So there is the whole literature on various ways to connect the beam model to matrix models, and I think this literature can be filtered past the lens of twisted holography for interesting, to get interesting constructions. So I don't know exactly what is the limit of what can be, what can be accomplished here. The chiral algebra looks simple, but there is a lot of structure in the states that you can insert at each point on the sphere. And most calculations actually, are, so if you insert complicated enough states, you can get calculations that are definitely beyond the current matrix model techniques. So you can get multi-matrix models and things like that, which at the moment we don't know how to solve. In trying to do we've been trying to do calculations involving these operators built out of order and square fields, and we're struggling against the limitations of the current matrix model technology. I'm happy to discuss this more in the questions afterwards. But for now, I'm going to restrict myself to operators of size n, which do not deform the geometry, but insert D-branes in the holographic dual. So they tell you, I want to have a D-brane that arrives at the boundary at a collection of points, and then you need to figure out how to fill in the picture. So, right. So the operators that are relevant for this context are called determinant. Call them determinant operators. I call determinant operators. They are what you get if you take a determinant. So they're sort of BPS determinant operators. You take a certain null combination of the scalar fields of the nickel phosphor mills, this n.5. Maybe you add the multiple of the identity, and you take the determinant of that. So you get a certain superposition of polynomials in traces, if you want, but of order n, which depends on this parameter m and on this direction n. And these high-BPS giant gravitons are known or conjectured to be dual to the insertion of a D3 brane of a specific shape near the boundary. This D brane is called a giant graviton. It wraps an S3 inside S5 and looks like a line approaching the boundary in a DS5. This parameter n essentially determines the orientation. It tells you which S3 are you looking at inside S5. And this parameter m tells you the size of this S3. So that when m is equal to 0, you get a maximal S3 inside S5. And when you increase m, the sphere becomes smaller. And my objective is to study the correlation function of multiple determinants and the large n within the chiral algebra subsector. So in the physical theory, the expectation is that, as I'm saying, each determinant of insertion tells you that there is a D3 brane arriving at the boundary in a certain way. And then the correlation function should be at large n controlled by, in large Hooft coupling, controlled by a D3 brane wrapping some form manifold in this 5 times S5, which approaches the boundary in this specified way. And so in the bulk, the calculation should involve essentially open-closed type should be string theory, where you have both closed strings propagating about, but also open strings living on M4 and interacting with the closed strings. And the sort of basic calculation one could do in this setup is to say, I put a trace at some point on the sphere, I put a collection of determinants, and maybe in the large n limit, this will be controlled by a closed string propagating from the boundary to the D-brane saddle. The crucial subtlety is that the same boundary conditions on the D-branes might result in many different types of saddles. So there might be many different ways of filling in with the D3 brane these asymptotic tubes that are coming in from the boundary. You might have completely disconnected saddles where each tube sort of closes off at some distance from the boundary. You might have partially connected saddle where some tubes connect each other and some close off. And then you could have perhaps this sort of amoeba where all tubes come together and merge. Each of these solutions in the physical theory will have its own action. And the final answer will be a sum over exponential terms dominated by by one of the saddles, and which saddle dominates will depend on the parameters. And as you explore the parameter space, presumably different saddles will kick in and get in and out of the problem. There will be Stokes phenomena and so on. Of course, in the full physical theory, it's yes.
You're talking about the Green-Schwarz superstring or the Nevu-Schwarz superstring?
I'm talking about type 3 string theory in DS5 times S5. Pick whatever description you want of the theory.
What I'm concerned about is, don't you have problems with the 5 form, the usual problems with the 5 form?
Meaning?
In the ADS5 cross X5 background, you have the 5 form, right?
Yes.
You have a non-trivial 5 form. So usually it's not known how to formulate the string theory on such a background.
Oh no, absolutely. I'm not saying that I will do this calculation. I'm saying, in principle, in the physical holography, this is what one should be doing in order to match large n behavior of determinants. At the moment, I don't think there is any computational technique to compute the correlation function of determinants at strong Hooft coupling in the QFT. And as you're saying, there are also, of course, challenges in doing the calculation in this 5 times S5. I don't know if, but this is right. But all I'm trying to say is that even at the leading order in N, there is this subtlety that there would be multiple saddles on both sides. And a basic holographic conjecture would be that you can, if you could compute the correlation function on the quantum field theory side, you should be able to see saddles which are in one-to-one correspondence to the possible D3 branes, which on the gravity side fill in these tubes. And actually, it would be an interesting question of which of the D3 configurations can actually contribute to a given correlation function. Now, as I said, so I'm not going to do this calculation in the full physical theory, of course, that's beyond my abilities, but I can try to take determinants which happen to live in the chiral algebra subsector, and I can try to see what happens in the twisted holography. So essentially, as I was mentioning, right, here in the chiral algebra subsector, you pick some linear combinations of four of the scalar fields. You can just put those specific linear combinations inside your determinants. So I'm going to study something like determinant of M plus X plus Vy. So in the chiral algebra subsector, I'll have determinants which depend on now 2 parameters plus the position, so 3 parameters, the position Z, V that controls the linear combination, and M that controls the size. The correlation functions of a collection of determinants are going to be rational functions in Z, just free chiral algebra correlation functions, and they're going to be polynomials in these parameters V and M. But somehow you would like to see that in the large N limit, you get an e to the minus n behavior with multiple saddles, which can have a geometric interpretation. What were the 3 branes in the physical theory should become the 2 branes in the B model, essentially things that wrap an holomorphic curve inside a 3-dimensional complex geometry. And these parameters M, Z, and V control some endpoints of these D branes as they approach the band infinity in SHUC. Along some C star. And as I say, what I want to do is to really try to match saddles between the quantum field theory and the B model. So I want to find the saddles in the quantum field theory, and I want to match them with holomorphic curves in SHUC. And I want the match to be exact, at least in the linear order in N, as a function of this parameter N, Z, and V for each determinant. Now, if we had the full dictionary between twisted holography, between sort of the B model and supergravity, I could then take these saddles in SHUC and promote them or lift them to actual saddles in ADS 5 times S5. And I think that would be very interesting. At the moment, I don't know how to do so. So the calculation of the quantum theories is done using the free quantum field theory. And luckily, these authors, Gianco, Mazzo, and Vescovi, had just studied the problem of correlation functional determinants in a free theory. For them, the purpose was to sort of use this as a springboard to a full calculation at all values of tooth coupling, perhaps using integrability. In the twisted holograph setup, we can just stop at the first step and take the free field theory calculation and study it. So they have a very nice way to study the problem. The first step is to fermionize the determinants. So you take this determinant of an n by n matrix, you write it as the Grassmann integral, introducing these auxiliary fields, these auxiliary fermions, psi and psi bar, which are sort of n zero-dimensional fermions, such that the integral over psi and psi bar reproduces the determinant. So you sort of give these fermions a quadratic action proportional to m, x, and y. So you can give a physical interpretation to this in terms of the string stretch between the giant gravitons and the original branes. I'm not going to get into that, but it's a very convenient technique because once you fermionize all of your determinants, then the correlation function of a collection of determinants just becomes a correlation function of a collection of exponentials in the x and y fields. And this is easy to compute. Once you integrate away the x and y fields, you end up with a quartic action for the fermions. It's just you get a finite dimensional integral over sort of k copies of this psi psi bar, where k is the number of determinants, with an action which is quartic. And then you can apply, their idea is to use the Hubbard-Stratonovich transformation, where you essentially introduce some extra auxiliary fields, a matrix of size k, or bosons, which integrate in a way to make the path integral of the fermion Gaussian. And then you integrate away the fermions, and you end up with just an effective action for this auxiliary field rho. So an effective action for a k by k bosonic matrix rho. Now, this effective action has sort of two terms. One that came out of sort of just the classical correlation function. So you had the quartic term on the fermions and some quartic action for rho, the quadratic action for rho, which depends on the Green's functions of the fields x and y. And then there is an extra term that comes from integrating away the fermions. These fermions coupled to rho with the quadratic action, something like psi bar rho psi. So when you integrate away the fermions, you just get the determinant of rho to the number of fermions, which is n. So you get one loop term. It's something like the determinant of rho, but to the power of n. And so your action has sort of two terms, both of order n, one classical and one loop. And so you get an on-trip, you can sort of, in the large n limit, you can then study the behavior of this setup by looking at classical saddles for this action for rho. And this was the proposal of Jan Komatsu and Vescovi, that somehow the classical saddles of the action for rho should be identified with essentially the geometric saddles on the holographic dual side. I think in the physical theory, this is a tricky statement, because it's not clear that as you turn on the Hooft coupling, sort of rho will be the correct auxiliary field to add, but it's definitely a very natural statement in the free theory. So before I was understanding what to make, before I move on just a second. Well, okay, I will say it later. So how do the saddle equations look like? In the particular case of the chiral algebra setup, the saddle equations simplify a little bit. The original saddle equation in Jan Komatsu and Vescovi are equations for a matrix, but they're not matrix equations in the sense that they involve operations that are more complicated than multiplication or inversion. But in the chiral algebra setup, there is a very neat simplification, and the saddle equations can be written in the simple form. So let me denote as zeta the diagonal matrix whose entries are the positions of the determinants on the sphere. Let me denote as mu the diagonal matrix whose entries are the orientation of the different giant gravitons. Then the saddle equations become simply the commutator of zeta and rho plus the commutator between mu and rho inverse equals to 0. Intuitively, the rho inverse comes in because when you integrate the fermions, you get its determinant of rho to the power of n. That becomes the exponential of the logarithm of rho. And so when you look right down the saddle equations, the derivative of logarithm of rho is the rho inverse. If you find a solution, yes.
So when you do the Hubbard-Stratonovich transformation, you would in general get a kinetic term for the rhos also, right?
Yes, that's right. So you get the kinetic term for the rho.
Yeah.
Yeah, absolutely.
So you would have. Why doesn't the kinetic term appear in the equation of motion?
Oh, it does. So right. So here. So this moved a little bit. I'm for some reason I dropped the formula. I don't know where it went. But so these are the saddle equations in a general setup. The ones derived by Jan Komatsu and Vescovi. So essentially they set up rho inverse to be equal to the product element-wise of rho and of the propagator, the Green's function between the linear combinations of fields which appear in two of the determinants. This is what comes from the kinetic term you're mentioning, and this is what comes from integrating away the fermions.
Okay.
In this particular situation of the chiral algebra, this G actually looks like sort of VA minus VB over ZA minus ZB. So I can move the ZA minus ZB to the left, and it, sorry, there was, anyway, so you end up with something like a difference of two things multiplying rho, AB, and a difference of two things multiplying rho inverse, AB. And you can write that as a commutator with diagonal matrices. So this is how the Saddle equation here emerges. So there is an important simplification. The equations are hard to study in the general setup, even for free Yang-Mills theory. It would definitely be interesting to study them more in detail because, if you have a proposal for what the holographic dual is of free Yang-Mills theory, then you should be able to match the Saddle equations with D-branes in the holographic dual. Absolutely, it would be interesting to understand this more generally. But in the case of the chiral algebra, there is a simplification, which was a key. So you see, when you look at it, when you see equations involves sums of commutators equal to 0, they remind me of the sort of equations you find in integrability, like Kitchen equations, which usually come from some kind of a lax matrix. And so with Kaja, we played around a little bit, and we tried to rewrite this equation as the equation for the commutation of two matrices. So we observed that if you build matrices B and C, depending on a spectral parameter A of this form, A mu minus rho and A zeta plus rho inverse, then the Saddle equations become equivalent to the statement B and C commute. Another property of these matrices B and C is that the product BC, because there is a rho and rho inverse, has a 1. So you can define a new matrix D so that AD minus BC is equal to 1. Okay, so every time you can find a solution of the Saddle equations, you can also find this collection of three matrices, B, C, and D. We satisfy this relation. Why is this interesting? Well, because now you can study a spectral problem, find a spectral curve. You can say, okay, for each A, I diagonalize B, C, and D. I can do that because they commute. So I look for a simultaneous eigenvector of B, C, and D. This will have eigenvalues, little b, little c, little d. Is a very A, I get k copies of these eigenvalues. So I'm going to get some kind of a curve as a function of A, as a very A k-sheeted cover of the plane. And because of the relation AD minus BC equal to 1, this curve actually lives in SL2C because its eigenvalues will satisfy a relation AD minus BC is equal to 1. So out of a saddle in the chiral algebra, the quantum field theory, we get the equation for an holomorphic curve in SL2C. And SL2C, remember, was the holographic dual of the chiral algebra. So you get immediately a possible candidate for the holomorphic curve, which describes the various saddles. And so we conjecture that this is indeed the holographic dual curve, and then we check it in various ways. The first check is that it has the correct asymptotic shape as it approaches infinity. So this holomorphic curve really goes to infinity in the form of these tubes with specific orientation. If you're given a solution, a saddle solution, there is a way to study the action of the saddle. Of course, you can write down an action as a function of rho, but even better is to look at the derivative of the action with respect to these parameters m. So it turns out that the m's are the diagonal components of rho, and the conjugate momenta are the diagonal components of rho inverse. So if you understand, so this allows us to get to a geometric interpretation of this. and really match the action of in the large N limit of the quantum field theory saddle with the action of the D-brane on the bimodal side. We also studied the analog of this problem. We take a closed string insertion, and we really take a propagator going from the insertion to the D-brane and integrate it over the D-brane, and we match the expectation value of a trace, of a single trace operator in the background of the determinants. And finally, we checked the sort of global symmetry algebra identified with Kevin acts properly on both sides in a way that matches. And we did some one-loop checks too. So all in all, I feel really confident that our conjecture is correct and that we found a way to identify the correct D-branes starting from the saddle point equations, the quantum field theory. So what sort of things would be nice to do next? First of all, at the moment, we're not sure that every curve in SL2C can be written as a spectral curve. We proved it for genus 0, but we don't know if it's true in general. So in general, in this holographic setup, it would be nice to know which saddles on the gravitational side actually contribute to the quantum field theory calculation. When you study twisted holography, there is also the extra challenge of figuring out which saddles of the twisted gravity setup can be lifted to saddles of the gravity setup. So both questions are kind of interesting, and it's not obvious that all saddles. So this means that it's not obvious that all saddles on the bimodal side contribute to the correlation function. So it would be nice to know if that's the case. Yes.
So the holomorphic curves usually mean usually correspond to some genus G Riemann surfaces, right?
Yes. Yes.
So what bearing does that have here?
So the short answer is I do not know. So at the moment, for when the surfaces of genus 0, we can show that every surface of genus 0 in SL2C is the spectral curve for some rho. At the moment, I do not know if that's true for curves of general genus. I think a spectral curve can have genus different from 0, but we don't have many explicit examples of solutions for rho. So again, I'm not sure. I would like to understand this better. It would be nice to match the 1/n corrections to these statements. In principle, so this is mathematically rigorous on both sides. It should be possible to really prove that the large N expansion, the 1/n expansion around the saddle on the quantum field theory side matches the BCOV theory in the presence of a D-brane on the bimodal side. I should say that, by the way, the the 1/n expansion around the saddles, lives in the general umbrella of the Hooft expansion, but it's not the standard Hooft expansion. So I would like to understand a little bit better how things work. So if you do the standard Hooft expansion of the correlation function, what you land on is sort of this saddle where all the D-branes are disconnected. And this procedure of integrating in auxiliary fields and looking at the saddle of rho somehow allows you to explore other saddles, but I don't fully understand the Hooft expansion, how the Hooft expansion works in that context. I think it would be nice to understand it a bit better. Another point is that this is just one of the examples of twisted holography. There are a lot of Fordini-equal true theories which have holographic duals, and they have chiral algebras too. And one can study, this gives rise to a variety of extensions of the setup I discussed in this talk. And then there are the other twisted holographic examples involving M theory and whatnot. And for all of those examples, you can study determinants and the corresponding D-branes. Yes?
Oh, hi, Davide. Hi.
Hi.
So I was waiting for you to finish so that I can ask the question.
Okay,
but,
okay.
Yeah, maybe later is fine.
The fourth point is that, as I said, I would really like to know, given a spectral curve in SL2C, how to get a deep brain in the Spacetimes S5. I think this should be definitely doable. There is a well developed general story on how to associate supersymmetric deep brains in the Spacetimes S5 with holomorphic objects by Mikhailov. But Mikhailov's work does not seem to be quite covering this particular example, so it would be nice to extend it. I think knowing the D3 brain shapes would also help extending this work beyond the chiral algebra setup. I could study things like a correlation function of chiral algebra determinants, but in the presence of single trace operators which are outside the chiral algebra. It might be possible to study this problem. Sort of try to start, or maybe operators which are close to being in the chiral algebra. So it might be possible to have some kind of near chiral algebra expansion, where perhaps the Hooft coupling is multiplied by some small parameters, so that the perturbative expansion is manageable. And finally, right, the big project is to understand situations where operators are order n squared instead of order n, so that you're really inserting non-trivial geometries and finding non-trivial gravitational saddles. And that's very much in progress, but it's tricky. Okay, I think this is all I wanted to say.
Well, let's thank Davide, and then we'll move to questions. Maybe just thank you, Davide.
Hi,
Abhijit, go for it.
Hi, Davide. Thanks a lot for a fantastic talk. So I have two questions. One is about whether one can study the twisted holography in the context of lower supersymmetric operators. So here you worked with the chiral algebra sector, which preserve more than is not the minimal, let's say preserve a certain supersymmetry. These are the sure operators and so on. So, but is there a way to do that even for less supersymmetric operators? Let's say 1/16 in n equals 4, 1/8 for n equals 2.
Yes, absolutely. So the 1/16 BPS operators are precisely what's captured by the holomorphic twist of n equals 4 super mills. And I've been looking at the problem a little bit. There is nice work by done by Meanwhile and collaborators first, and then also some nice work by Sheen and his student. All of those calculations can be carried over to the holographic twist, the holomorphic twist of n equals 4 super mills, and we're trying to understand if it's possible to push them further using this holomorphic twist technology.
But what is this bulk you would have in mind in that context?
So the bulk, as far as I know, it's a sort of a 5-dimensional version of the B model, which Costello and Lee introduced at some point. I don't understand it very well yet. It's BCOV theory somehow in 5 dimensions instead of 3. But the back reaction is less easy to understand. So in the context of this chiral algebra setup, you had a 3-dimensional B model, and the 3-brain back reaction turned on a complex structure deformation. So that is easy for me to wrap my head around. I take C3, I deform it to something else, I get SL2C. But in this 5-dimensional setup, the D3 brains source what I think it's a non-commutativity, some kind of a position-dependent non-commutativity. And so at the moment, I don't think people know how to describe the full holographic dual geometry.
So sorry, just to ask you further about what you just said. So how do you think about the SL2C in this chiral algebra sector? Because in what sense the chiral algebra lives at the boundary, let's say, of the SL2C? Or
it's just a standard holographic dictionary.
It's what? Sorry?
It's just a standard holographic dictionary. It's not that the chiral algebra lives at the boundary as much as B-model correlation functions with boundary deformations are equal to the chiral algebra correlation functions.
Okay.
But if you were trying to so what you can do is to try to derive this correspondence using the same strategy as Aninda Sinha did for the full physical correspondence. So instead of the 3 branes in R10, you would study holomorphic branes, holomorphic D2 branes in C3, and these backreact the geometry, and the backreacted geometry is SL2C.
Oh, I see. That's what you said. I see. Okay.
Yes.
I see. Thanks.
But if you try to do the same thing for the holomorphic twist, then you need to backreact C5 with this non-commutativity, position-dependent non-commutativity.
Okay.
And if you want to understand the result, then you could do finite. You could do some more interesting.
And this back reaction for the case of D3, this holomorphic D2 branes to give rise to this SL2. So this has, what is the reference for this?
So with Costello, we do the calculation, but this goes farther back. For example, the whole story about the relation between resolved conifold and deformed conifold was based on a similar procedure where you put these 2 branes wrapping a CP1 in the resolved conifold, and you claim that you get the deformed conifold.
Thanks a lot.
Okay, any other questions, comments?
I have a question. So you got the...
Go ahead, and then there's Kaushik. Yeah, go ahead, Shomdat, and then there's Kaushik. Go ahead, please.
Yeah, so you got the action for the rho by subsequently integrating out and integrating in some fields, right?
Yes.
So once you have the solution for the rho in terms of the A's and the B's, can you sort of reverse engineer the process and integrate in and integrate out to get back the original action in terms of the X's? And then you would have a sort of handle on what kind of theory the solution looks like in the original variables. Would that be sort of some sort of help?
So right, it's not clear to me exactly what that concretely means. So see, giving a VEV to rho essentially means that you're studying a situation where there is a fermion, a VEV or the fermion bilinear. And I'm not quite sure how to follow that all the way back.
You have the VEV, right? And you can always expand around the VEV.
Right, but that's a tricky thing, right? I don't know how to expand around the VEV of a fermion, right? It's a VEV of the fermion bilinear. So you're using this VEV of rho to sort of encode a slightly non-perturbative phenomenon where
rho is a scalar.
Rho is a scalar. Yes. So if you can definitely sort of write down an action which has rho, size, and axis without integrating away rho, size, and axis, and then give a VEV to rho, and then Hooft expand that. That's definitely something you can do.
Yeah, maybe.
Kaushik, go ahead, please.
Sorry if I missed something, but about your first question of matching spectral curves of SL2C with all curves, under constraints on the degree of spectral curves for SL2C, which in turn will restrict the genus? Or I'm completely mistaken?
I am not sure. So I should definitely learn more algebraic geometry. So at the moment, it's not quite clear to me what are the constraints on the possible genus or properties of the spectral curve.
I mean, after all, it's even dimensional thing. So yeah.
So right. So we're studying one-dimensional holomorphic curve inside some compactification of SL2C, which intersects the compactification divisor in a specific way.
Yeah. So how do you get higher degree spectral curves in SL2C?
I'm not sure what the degree is here.
So if I start writing down the usual spectral curve in SL2C, what is the representation that you choose here?
I'm sorry.
I mean, you ordain the usual spectral curves of SL2C, right?
I don't know what the usual spectral curves of SL2C are.
I mean, the spectral equation gives you some curves in SL2C with certain kinds of singular. I thought there was a classification of Bovill which studied that. So, and if I remember that doesn't have all the degrees.
Okay, I know nothing about it. I would love to. If you have a reference, I would love to.
Okay, Bovill had this reference. I can probably send it to you later on. I don't have it.
So Bovill, you said?
Yeah, Bovill had some classification.
Can you maybe write the name in the chat so I don't.
BAUVILLE.
Write it in the chat, Kaushik, if you don't mind. And let's take the last question while Kaushik is doing that from ICTS. Then we'll have to close. Go ahead, ICTS.
Hello. Hi. Am I audible?
Yes.
Okay. So I just wanted to ask a question about a comment that you had made about the relation between the B brains and the D3 brains.
Yes.
Can you expand upon it in the sense that what data should be compared to actually understand how the mapping goes? Is it understood? Like what calculation one should do to say understand which B brains correspond to D3 brains?
Yes. So the correct answer would be I don't know. Worse, I have an intuition which might be wrong. So my intuition is that SL2C is ADS3 times S3, and this ADS3 times S3 is a locus inside ADS5 times S5, which is preserved by some symmetries. So there are two rotations which are also preserved by the setup, and the fixed locus is in ADS3 times S3. And then, according to this intuition, the holomorphic curve could be the intersection of this M4 with that SL2C, with that ADS3 times S3. But I do not know if this intuition is correct. It might be incorrect. A better statement would be that somehow, again, the kappa symmetry constraint on the D3 shape gives you some geometric data, and that the geometric data somehow is encoded in the holomorphic curve. But yeah, I really understand this much less than I would like.
Okay, thank you.
Okay, well, friends, let's thank Davide once more. And thanks a lot, Davide, for a great talk. And before we close, I'd like to once more thank all the organizers, Aalok, and everyone from Roorkee and the entire organizing team. Thank you all very much. It's been a very exciting conference. We've learned a lot. And look forward to meeting again next year for the National Strings meeting. Thank you all very much. Aalok, do you have anything to say as the last? You have the last word, sir.
No, thank you. Thank you, everybody. Thank you so much. Thank you.
Thanks to you and all your team. You did a wonderful work.
Thank you so much. Really appreciate that. Thank you. Thank you very much. Thank you so much. Thank you. Please stay safe. Thank you.
Thank you all.
Yeah,
Bye.
Bye-bye.
Take care. Bye.
And a happy new year, I guess.
Right. Happy New Year. Happy holidays, everyone.
Happy holidays. Yeah.
Bye.
Thank
Bye.
you, Alok. Thank you, Alok.
Thank you. Thank you so much. Thank you.